Yeah, welcome. The problem that Marabou is trying to solve is that verification of deep neural networks. So it assumes that it has as input um, a fully connected feed-forward neural network, which has piecewise linear activation functions. So here on the slide, we can see an example of such a network. So the connections between the layers are obviously weighted sums, so they present those are linear constraints, whereas the activation functions are piecewise linear, um, which is to say not strictly linear, right? So when it comes to verification of such models, there are two types of properties that we want to show. Typically, um, one's one set of properties are reachability properties, which have a shape of, okay, if we assume that input is in a certain range, can we guarantee that the output will never be in some range that we deem unsafe? And now how we specify these ranges uh, can take many forms as long as it can be expressed linearly, right? So the relationship can be a relationship between the output labels, or it can be just a numerical threshold on the output. Reachability properties usually stem from some form of specification. So we have a problem that we want to solve, and we have some idea of what are the properties that a solution to that problem should look like. So then we can try and write down such properties. This will, however, not always be the case, right? If we think of perception networks, it is kind of difficult to specify some of their properties. What does it actually mean for a cat to be in the picture and so on, right? So in those types of cases, we would focus on robustness properties. So a robustness property is basically given a fixed input-output pair, which we know the kind of like a labeling of an input point, then we are interested in whether there are any um, essentially adversarial examples in some delta neighborhood, right? So we're looking at an input that is close to the fixed point, and we want to show that all such inputs will have the same label. If they don't, and we find a counterexample, then that would mean that we have actually found an adversarial example, right? So um, here we're talking about Marabou, which takes as input now a network and a property, right? And as output, it will either say, okay, this property holds for all inputs, or it will find a satisfying assignment for the constraints, which would essentially be a counterexample. Yes,
May I ask a question? So you
of course.
consider the local robustness, right? Or
Can you repeat that? I'm sorry.
so you consider here the local robustness, right? Not the global robustness.
Yes, local robustness. Global robustness, I mean, we could try to solve it. It can just be encoded essentially by duplicating the network and so on. But in general, it's a much harder problem and even less likely to hold than
Yeah,
the
definitely.
local robustness properties. Yes. In
And
terms of being able to handle it, the tool can definitely handle such properties too. It is just a matter of like encoding the problem, right? Um, so Marabou is actually a re-implementation of the Reluplex algorithm, which a guy proposed in 2017. And Reluplex is essentially simplex with native support for ReLU constraints. And then it's also augmented with a lazy backtracking search. You can also think of it as an SMT solver where different piecewise linear constraints represent individual theories. This base algorithm is now also bolstered by a more meta algorithm, which we call split and conquer, which tries to improve the scalability or tries to decompose verification queries dynamically. And we'll look into detail how this algorithm actually looks like. It's actually fairly parametric, so one can shape the search in various ways, and it's actually highly amenable to parallelization. So Marabou is actually available from GitHub, and if we were to go here just for a moment, yeah, I mean, it looks like any repository, but the README has all the information about the tool that you may want, like how to obtain it, how to build it. The tool builds on both Linux. Our main support is on Linux. It works also on Mac OS and Windows, but it's not guaranteed to work on all flavors. Anyway, back to the slides. So in terms of technical features, right? So networks are assumed to be fully connected feed-forward neural networks, and it admits also convolutional networks encoded as such. And it requires that the activation functions are piecewise linear. So it started with support only for ReLUs, but now we also have support for max, abs, absolute value, sign constraint, and so on. The tool can be used from the command line or using a Python API, and it can run in both sequential and parallel modes. So networks can come in a particular format called MNet, but also in TensorFlow's protobuf or ONNX. Whereas properties can be specified in a textual format, which we'll look into in detail, or can be provided programmatically through the API. Okay, so when we think about the VNN problem, right? So it has a linear part and a nonlinear part. The linear part is essentially connection between the layers, which are, and it's basically weighted sums, right? So these are purely linear constraints. And we can try and solve them using the simplex algorithm, right? So these constraints are basically written down in the tableau, and they are represented, all the involved variables are split into basic and non-basic variables. So here a row, for example, represents that variable x is equal to -2p plus 1q, right? And now below the tableau and to the side of the tableau are constraints that we may have over these variables. The yellow strip here actually represents the non-basic variables, and these variables are going to be the sort of knobs of our search. We will be assigning values to these variables, and in turn, we will be able to calculate the values of the basic variables. And the goal is, of course, to keep the assignments within limits, right? And then there are also nonlinear constraints, which we will kind of initially set aside until we solve the linear subproblem, and then we will actually consult the nonlinear constraints. Here, both examples are actually just a ReLU constraint connecting two variables. The left one connects variables P and R, and the right one variables S and T. So simplex will start with initial assignment of 0 to all variables. And in this case, we can immediately see that the lower bound for variable P is violated by this. So the way simplex would actually fix this is it will perform an update operation, right? So all it needs to do to fix this is to just bump the assignment up so that it actually meets the lower bound of 0.5. So after the update, all the non-basic variables will be within bounds. But now when we actually go and compute the value of variable x, we will discover that it is now out of bounds because we have -2 times 0.5, which is -1, right? So since the basic variables are essentially dependent, we cannot really just modify their assignment because we wouldn't really know how to distribute their value across the component variables. So what simplex does here is it performs the pivot operation. So it basically takes this row, which says x is equal to -2p plus 1q, and flips it around to now expose the variable x as one of the non-basic variables, right? So now the tableau will, basically the rows and columns will swap places, and the relevant coefficients will change accordingly. So then we will look at the tableau will now look like this, right? And now this broken bound is in the non-basic set of variables. So now we can just again perform an update and see what happens, right? So we will be performing a sequence of updates and pivots as needed until we actually find an assignment that satisfies the linear constraints, as is shown here. And now that we satisfy the linear subproblem, now we can consult the nonlinear constraints, right? And if we look here, in this case, the first ReLU constraint will be satisfied. So the blue ReLU here is basically P and R both have the same value, which satisfies the active phase of a ReLU. However, the red ReLU is broken because S and T are, they either need to be both positive and equal, or S needs to be negative, or T needs to be negative and S needs to be 0. So here we have two options. We can try and bump the assignments using an operation similar to update, or we can break down the ReLU and choose a phase that should hold and add it to the set of constraints. The algorithm is actually ReLUplex algorithm will try to repair a ReLU using the assignment about 20 times before it ever tries to break it down. But here, for the purposes of illustration, we will break it down immediately. So we're actually going to perform what is called a split. And that is to assume that, okay, let's say that this ReLU should be in its active phase. So we will assume that T should be greater than 0 and that S and T should be equal. So now when we provide this additional information to the tableau, the solver can actually figure out that variables S and T should have the same value. So it will split the previous value into 2 and obtain a satisfying assignment. Are there any questions so far? Is this going okay? Am I going too fast?
Super clear.
Okay, great. Okay, now let's take a look at a concrete problem. So ACAS-XU is a set of benchmarks that comes from, it's an implementation of the aircraft collision avoidance system for unmanned aircraft. And the input is basically geometry of 2 airplanes in flight, which have some distance between them, denoted by rho here. And then they have their own headings and relate to some fixed arbitrary position 0 and their velocities, right? And based on this, the neural network is supposed to, or well, the system here implemented using a neural network is supposed to produce a recommendation for what action needs to be taken. So here in this little policy plot, we can see COC, which denotes clear of conflict. So if the intruder is in this white area, the network would advise that, yeah, we can stay on our course. We are not in any danger of collision. In the light green area, the network suggests that we should take a weak right. In the dark green area, we should take a strong right. Conversely, in the blue and gray, it should be strong left and weak left, right? So this system is actually implemented using 45 neural networks because of some practical constraints, such as recall time and trying to make them small enough to fit onto unmanned aircraft. And each of those networks consists of 6 hidden layers, and each layer has 50 ReLUs. So as we can see, each network has 5 inputs and produces 5 outputs, and has about a total of 300 ReLUs inside. So what are the types of properties that we may want to check about this kind of network? So in general, property specification in machine learning doesn't often come so easily, right? We are often using machine learning to solve problems that we can't precisely define. However, in this case, neural networks are just one way to implement a solution for this problem. So what we can do is we can look at other solutions using, say, a table solution, lookup table solution, and infer kind of what the properties should be in that system and see whether they translate to the new system. So for example, here we have property phi1, which says, okay, if the intruder is far and it's moving slow, well, then clear of conflict should be a fairly low value. Here, maybe I should mention that the network will choose the outcome with the lowest value, right? So basically, this would say if the intruder is far and slow, well, clear of conflict should be a very high priority recommendation. Not high priority, but high on the list of recommendations, right? Similarly, if the intruder is far and slow, well, clear of conflict should definitely not be the worst ranked recommendation, right? And here we'll look also at the properties phi3 and phi4, which say that, okay, if the intruder is close, then we're never clear of conflict, right? If we're actually in imminent proximity to an intruder, we should be taking some action. We don't know what that action is, or we cannot say what it is, but it should never be do nothing. Okay. So let's take a look at how now we can actually write both the network down and the properties, right? So here I have one of the ACAST networks written down in the NNet format. So the format is basically just a sequence of values, right? Where the first row consists of the specification of the number of layers, number of inputs, number of outputs, and maximum layer size. And here, inputs are not counted as layers, right? So we have 6 hidden layers and 1 output layer, so for a total of 7. And then we have a specification of all of size of each individual layers. So here it's uniform, so it's not particularly interesting, but in general, right, we could have networks with varying size. Here we have lower bounds and upper bounds for the input values. And then we also have some normalization information, such as means of inputs and output, and as well as range of inputs and output. So the NNet format will often take values normalized, which kind of makes it tricky to write down the properties, right? So if beyond these first 6 rows, which are kind of like a meta information, actually follows the list of weights, right? Weight matrices between each layer, and then also bias for each layer. So now it's just a long string of matrices and vectors for the remainder of this file. So when we now want to say something about this network, we want to go and write down a property, right? So here we will try to write down the property phi3, which says, okay, if the intruder is close, then never clear of conflict. And here we can see basically what are the constraints. So this is just a plain text file. I've broken it here down in a way to make it easy to systematize. So x0 refers to the parameter rho, which is the distance between the 2 aircraft. And here are some relatively small values given, but the value here is not really telling because of the normalization. So this makes it kind of difficult to read, right? Then own heading is fixed to some value. Intruder is allowed some leeway in their heading, and then the velocities are have some freedom, right? So we want to now kind of the intruder is close is essentially encoded in this first line here. And now we want to say, okay, we will never choose clear of conflict. So the output labels are denoted by variables y0 to y4. And now what we want to say is that clear of conflict, which is a label y0, is not chosen, which is to say it is not minimum, right? But if you look a little bit more closely, these constraints here actually express exactly that y0 is minimum. And you might wonder why that would be for a second. But essentially, the way we are checking that the property holds, which is to say that it is valid, is we are actually looking for satisfying assignments of its negation. So if the property phi holds, then its negation will be unsatisfiable, right? So what we're writing down here is actually a negation of the property. And if we find a satisfying assignment for the negation of the property, that means we actually have a counterexample for the property that we are trying to check. Okay.
May I ask a question?
Yes.
Okay. What happens if your model is lacking of time to find an answer? Like maybe it's satisfiable, but there is the network is too big, for example. How will it react?
Yes, so the tool is complete in the sense that it will always, is both sound and complete. So it will always come back with an answer. So it will always find a counterexample if it exists. It might just take a very long time to do this. So it's more a matter of practical scalability of ensuring that you receive an answer in a meaningful time. And of course, having a smaller model and a simple property helps a lot with this. But in principle, the method itself is always supposed to return a definitive answer, whether there exists a counterexample or whether the property always holds.
Okay, so in practice, there is no way to set a maximum number of branch and bounds or things like that?
Oh, you can limit the effort for the tool in a variety of ways. The simplest one is simply by time. And we will actually see, so split and conquer actually uses this type of limitation. It tries to solve the initial problem using some amount of effort. And then when it fails, it will break it down. So breaking down the problem will also allow other techniques such as bound tightening and so on to actually simplify the query. And then these may be many more, but smaller problems will actually be easier to solve than the big monolithic query.
Okay.
We'll
Thank you.
see this in action actually in a few slides.
Okay. Thanks.
Yeah, of course. Right. So we can just now take a look as to how this looks like in practice. So I'm just going to run the tool from the command line. And then we can just see what the output is and how, oops, wrong terminal. Is this large enough?
Yes.
Okay. So yeah, here we're just going to run Marabou. Here, you can explicitly state what the network is and what the property is. It will usually assume that the first argument is the network and the second argument is the property. And now if we run, just hit run and see what happens. Ooh, capital M. Apologies.
The demo effect.
Yes. Did I mess something up now? Of course I did. As many times as you run things ahead of time. So I want to run, okay. Okay. So once we start solving, we will see, it will immediately output some information. So what is the actual number of layers in the network? What is the input layer size, output layer size, total number of values, how many variables it takes to encode the problem. So it's 610. So for every value is actually represented using two variables. One variable is how many inputs. One variable represents the input to the value, and the other variable represents the output to the value, right? And then we also have 5 variables that represent input and 5 variables that represent output for a total of 610 variables, right? And then here it will also output what are the initial bounds based on the given property, and then the tool will start outputting. statistics, which it will print out every 30 seconds or so. So what we can see here, let me just align this with the screen, is what is the elapsed time so far to solve the problem, how many simplex steps it has, what percentage the simplex steps are taking, what percentage the explicit basis bound tightening is taking, but then there are also other types of steps that are taking place, such as constraint matrix bound tightening, checking for degradation in case some numerical errors start rounding up. In that case, we may want to have to perform a precision restoration, how much effort are we spending on statistics, and so on. So it kind of like will give you a very detailed breakdown of various steps that are happening during the solving. And here we can see that actually the bulk of solving is spent between the simplex steps and the basis bound tightening. Whereas, for example, very little effort is spent into actually splitting the search space. So basically, the hardest part is still just satisfying the constraints. Among the statistics, there is all sorts of other information, right? So, for example, you can actually see how much various preprocessing techniques have managed to simplify the problem. For example, you can, in this case, they managed to eliminate 74 variables from consideration just based on the input bounds, right? Ideally, this is kind of was point of discussion during the workshop today, and that is just how much these deductive steps can help prune the search space, because every value that you have to consider is essentially you might eventually have to explicitly consider both states. So the more of them you can eliminate, the more you collapse the search space, of course. And so on. So we can see here some other statistics for the tableau. So how many pivots were performed, how many of them were real, how many of them resulted in faulty states, and so on, as well as how many. Here we can see the SMT core statistics, which show exactly how many different states were visited, right? So how many splits were made explicitly, and so on, and how deep the solver had to go, how many times it had to actually split on the value before it started backtracking. So yeah, and here we can see that this took about a minute of solving time. So any questions here? No, so far so good. Okay. We'll go back to the presentation for a second. So now let's take a look at what the split and conquer algorithm might look like. What's our time? Are we running out of time? We are. So yeah, the alternative solving mode is to solve things based on effort. So we try to solve a formula phi with some limited amount of time. And then if this time expires, we then try to break it down further into, say, 4 new queries, if we have maybe 4 cores at our disposal, and now allocate it a little more time for each of those queries. And say now 2 of those queries become simpler and we can just solve them directly, but 2 of them still timeout. So we're just going to repeat the step, right? Each of those timeout queries, we're going to split again, and increase the amount of time. We allot them until we either find one satisfying subproblem, because it will also be a satisfying problem of the original. It will be a satisfying assignment of the original problem, or until all the generated problems are unsatisfiable. So here there are several interesting properties, or several interesting things that one needs to note. Among other things, how many times we are going to split the problem initially, how many times you're going to split the problem during the solving. These things might be different. What's the timeout factor? So between 2 generations of problems, how much the time effort is going to be increased, and how many times we're gonna divide. So basically, every time we time out, we're going to split the problem into 2 to the power of n subproblems. And the question now comes how to split and which one, how to split the subqueries. For example, for those that have few inputs, we may want to just split the input range. But if we have something like a perception network splitting on what, 1,000 pixels, or who knows how many thousands of pixels, is not really going to be very consequent for the solving results. So instead, what we will want is we will want to actually solve to split on early ReLU phases instead. And then there are questions of, okay, once we choose how we're going to split, which one to split on, because there are multiple input ranges or ReLU phases. And the answer is that for parallelization to be effective, you want to generate parallel subqueries, because just one, if there is one peak, it will basically have to be the wall clock time that you have to spend. So I'll just go back to the command line, and we're now going to add some more parameters just to see what happens when we turn this mode on. So I'm going to add --snc for split and conquer, and then I will say initial divides to be equal to 3. This will split it into 8 subproblems, and we will also allocate 8 workers to work in parallel. And then we will see how much time it takes to solve this problem. In this mode, the statistics output will change. So now it will actually be showing which queries it has managed to solve, with which and which have timed out. And those which time out will then be queued, and they will be relabeled. So for example, query 2 timed out, and then we got a number of queries got queued, which are labeled query 221, 222, 223, and 224 respectively. And we can also see how many tasks are remaining. So the solving time went from 1 minute of wall clock time to 17 seconds of wall clock time, while kind of staying the same in this case with in terms of total user time. So the computer didn't really work any less for this, but the overall time decreased. If you want to play, you can actually just try and see now how different parameters affect the solving time. So for example, we can split more aggressively or less aggressively. So say we will split the queries after 2 seconds initially, and then we might actually see that this process of solving now many more queries actually time out, but maybe the resulting queries make up for it. We'll see when the output comes back. But yeah, here we've had to actually reach like depth 3 of partitioning, right? And the total time got worse. Now we actually solved it in 22 seconds, but yeah. Okay, since we're running out of time, I'll just go back and show you one more thing, and that is this web page where you can actually go and see various examples how to run Marabou using the Python API. So the page is sorry, which one of these is it? Here it is. Nope, I'll just click. That's what I designed it for. So this would take you to the documentation for the Marabou Pi API. So you have here in the sidebar a number of examples how to use the API if you have, say, NNet as input, TensorFlow as input, Onyx. I should maybe zoom this in. Yeah. And there are also examples how to run it in parallel also from the API, as well as detailed documentation in terms of what are all the possible options for various calls. These examples can also directly be downloaded as Jupyter notebooks that you can just run locally, assuming you have Marabou installed. Okay, since we're way over time, I am going to just open the floor for a few quick questions. Are there any questions? Interest?
Okay, so if no one is asking questions, I will take my turn. I was wondering, okay, I've tried to load a TensorFlow model directly into Marabou. And from what I understand, it's converted into a .NET format.
Yes.
I was wondering, is there any other way to okay, my question is, do you need to save your TensorFlow model to transfer it into Marabou, or can you have a function that take your TensorFlow models and consider a pre-built network in Marabou and just transfer the weights?
Yeah, I don't think we do that right now. So the thing is that, yeah, also, yeah, okay, for now, Marabou kind of mostly parses NNet, and then this Python API layer is kind of just intermediate step between that NNet input of Marabou, right? So we do not currently have any means of operating directly on any established formats, right? So what happens is that there is just a Python layer that calls eventually the command line tool, except that we've automated the process of this translation from your model to the tool. So what you could maybe try is, there is this feature of once you load a query into Marabou, you can force it to drop the query. So it can kind of export it into a file, and then you can maybe try and edit that file and work from there. But I'm not sure, it kind of depends on what steps take place by that point as to how that would be, whether that would be safe. It might be best to actually have an in-depth conversation about how we could achieve what you want.
Okay.
But there are workarounds. I just don't think that there are elegant solutions that in place right now for that.
Okay, thank you.
Yeah.
So I was actually wondering, if I now just pick my network and I want to have it checked, is there like some heuristics on how to pick the hyperparameters, such as the split factor that you just showed and these things? Or
yeah, right. If we look at this kind of like plot here, so ideally what you you want to shave away the first layer. If you can run multiple processes, you probably just want to split the query immediately, right? But then how much time to give? Like, if you notice that there are several generations of just timeouts, that just means that you need like bigger initial timeout, right? Or even if you don't, then maybe you need a more aggressive timeout factor, so that like if it times out with 5 seconds, it doesn't try with 7.5. You want it to try with maybe 25 next time, right? But a lot of these things, even for ACAS networks, which are conceptually the same, is actually very network dependent. So in a lot of ways, it requires a little bit of exploration ahead of time before you get a sense of, okay, this is now wasting time and this isn't wasting time, and so on. But in that sense, I think splitting to as many parallel threads as you have is reasonable, as well as just trying to not time out for more than one generation in a row. Right? If that is happening, then you probably want to increase either increase the base time or increase the time factor.
All right,
Those would
thank
be
you.
my rules of thumb to share. But yeah, it also
No,
highly
but
depends
it's already
also on the
very
topic.
helpful.
Yeah. Any
Thank
other
you.
questions? Okay. Yeah, thanks. I'll see if we can post these slides somewhere, or I might just host them on Marabou's page.
I think Giant will come back to you to know if he can share the contents of the workshop.
Yeah, and I'll also write down the queries that I kind of like had in mind to illustrate. But yeah, time with these things always runs out. Yeah, I mean, thanks for coming and thanks for your attention. And yeah, I mean, you know, GitHub is there. If you have any issues, kind of requests, a lot of the tool is being driven by need, right? So if there is something that you would want to see, it's best if you just write us a line. And you know, you might get an answer, we do not intend to do this right now, but we can at least maybe think of it in some future to put it on our roadmap to add to the tool. Okay.
Okay, so let's thank Aleksandar once again. Thank you for your presentation, and yeah, eager to see what Marabou is coming for 2021.